Okay, question 8 is on electric field, an electric field surrounding this positively charged conducting sphere. So this is electrostatics, right? So we're in this situation where all the positive charges, they have distributed themselves evenly on the outside surface of the sphere, and we have an electric field lines pointing outwards away from positive charge, and we have to explain why the electric potential decreases. Well, we have this formula for electric potential in the formula booklet, but that is the potential surrounding a point charge. Now, this is not exactly a point charge, it's a conducting sphere, but outside of the radius, the field is exactly the same as a point charge of same value Q at the center. So we can use that formula, and then we can say that, of course, Q is positive. Q is positive, and V is K. The potential is given by that formula. So as R increases in going from A to B, then V will decrease, as we see from that formula. Okay, have to draw the variation of electric potential. So yes, the variation is, as we have just mentioned, outside of the sphere. So we do have a hyperbola from R onwards that it decreases, approaches 0 like that, proportional to 1 over R. But what about inside the conducting sphere? Well, we have to remember that in electrostatics, the electric field inside of a conductor is 0, which means we have a constant potential. So don't forget that inside a conductor we have a constant potential. So the E is electric field is 0, V is constant inside a conductor. In the electrostatic case. Okay, we don't have any currents, continuous currents flowing through a conductor. So, proton is placed at A, released from rest. Magnitude of the work done as it moves from A to B is that many joules. We are given some distance values to point A and B from the center. Calculate the electric potential difference, PD, potential difference. It's work per charge, right? Work done per unit charge. So moving from A to B, this proton, this is the amount of work done by the electric field. And then the charge that we moved was just a proton, the elementary charge, 1.610 to the negative 19 coulomb, and that is going to give us roughly rounded off to 2 sig figs, 1100 volts. We do know that the potential itself is decreasing from A to B. So if you wanted to be very technical and careful, which we're going to be in the next question, then delta V is actually negative. The potential decreased, but this is the potential difference between points A and B. But yeah, now we have to be more careful as we determine the charge on the sphere. So let's write down delta V, the change in potential. So my final value is the value at B. My initial value was my value at A. Remember, delta is always the final quantity minus the initial quantity. And I know that's going to be equal to, and then I have to be careful here. I know that the potential decreases, and the potential decrease is 1.1 10 to the 3 volts. From this I can get Q. I can take QK outside of a bracket. And then I just need to do the math, rearrange that to get Q. Okay, so RB is 1, 10 to the negative 1. RA is 5, 10 to the negative 2, smaller, so that fraction is bigger, so I'm going to get negative times negative. Yeah, this is going to be reciprocal because I divided by it, divide by k, and this should come out as 1.2 10 to the negative 8 coulomb. And it came out positive, which it should. And then slightly silly question, so why do we develop a common terminology to describe fields? Well, kind of makes sense, doesn't it? But let's just say different force fields can easily be compared by using a common terminology. Something along those lines. Okay, that was that.